Gauge theories describe local interactions that occur in single spacetime points. Fields on spacetime often cannot be described simply by a map to a fixed vector space, but rather as sections of a non-trivial vector bundle. The fundamental geometric object in a gauge theory is a principal bundle over spacetime with structured group given by the gauge group. Lie groups, like the Lorentz and Poincaré groups, which are related to spacetime symmetries, and gauge groups, defining internal symmetries, are important cornerstones. The groups act on fields and leave the spacetime integral over the Lagrangian invariant. The fibers of a principal bundle are sometimes thought of as an internal space at every spacetime point, not belonging to spacetime itself. Gauge theories, which are field theories invariant under all gauge transformations, have the huge symmetry group of bundle automorphisms. The diffeomorphism group of spacetime plays a comparable role in general relativity. In the case of Minkowski spacetime, rotations correspond to Lorentz transformations. An active Poincaré transformation sends the world vector u at point O to a world vector v at point O hat. If the transformation also sends the tetrad at O to a tetrad at O hat, then the coordinates of u are the same as those of v. The abstract sphere y negative of past null directions represents the observer's celestial sphere in a natural way. The sphere S negative, or its projection to sphere S, gives a more concrete but less invariant realization. The stereographic projection sends points from the sphere S positive into the argand plane. For that purpose, choose the north pole as a point from which the map projects all other points in the sphere. Then the union of the plane and the point at infinity yields the Riemann sphere. Light rays reaching the eyes of an observer pierce a sphere centered at the observer's position. Specify a point in the celestial sphere with a latitude and a longitude. The geometry of the equation zeta equals the exponent of I phi times cotangent of theta half relates the spherical polar angles theta and phi to the complex stereographic coordinate zeta. In Minkowski spacetime, the intersection of the null cone with a plane yields a sphere. As the plane through curve segment ON varies, it provides the stereographic projection. The point P maps to point P prime. The parabolic intersection of the sectional plane with the cone has the same intrinsic Euclidean metric as the argand plane. A Lorentz transformation in Minkowski spacetime chooses an inertial frame for an observer. The properties of Lorentz transformations are best shown on the Riemann sphere because it has all the null directions of an observer. A proper rotation and a boost in the z direction combine together to make a force screw. A null rotation is a type of Lorentz transformation where a single point is left as the only fixed point. The rigid transformation of the argand plane projects to a transformation on the Riemann sphere. For the Riemann sphere, the points are displaced along circles through the south pole tangent to the y direction there. A null cone is in the tangent space of spacetime at point O. The representation of a spin vector requires a pair of infinitesimally separated points on the sphere y positive. A spin vector is shown in terms of points P and P prime of a null flag. The curve segment connecting point O to point N represents the temporal direction. The temporal direction is normal to a cross-section of the null cone. The angle between the temporal direction of the two sections determines a metric that measures lengths and angles. After a transformation in the linear space of the generators of the cone, the sides of triangles are multiplied by a scalar number. Construct a complicated object by annihilating and creating boundaries. Look at transformations in the tangent bundle in order to mark the orientation of boundaries. Follow the following 9 steps for building a vector bundle on the 3-sphere. Step 1. Mark the boundary of one copy of SO3 with 16 vertices of a hypercube. Step 2. Make a tangent frame at origin point O and parallel transport it to the marked points. Step 3. Mark the frames with identifier 1. Step 4. Parallel transport a triad from point O to a boundary point. Step 5. Switch coordinate charts from chart N to chart S. Step 6. Parallel transport the triad to the center of the counterpart copy of SO3. Step 7. Parallel transport the frame to the boundary points from the center of the other copy of SO3. Step 8. Mark the frames that are parallel transported from the center of chart S at origin O with identifier 2. Step 9. Compare them with frames originated from the center of chart N at origin O. The twist in frames 1 compared to frames 2 is like the reorientation of 3D objects in the Euclidean three-dimensional space. Even though both copies of SO3 represent the same 3D orientation, they are distinguished from each other as points in the special unitary group of complex dimension 2, SU2. The equivalence class of twisted frames at boundary points defines a group of rotations, SO3. The clutching construction makes an associated vector bundle on the three-dimensional sphere, S3. The construction creates a vector bundle through a continuous function denoted by f. The clutching function resolves the conflicts of tangent frames along the boundary. It does so by producing an image in SO3 given an element in SO3 cross SO3. A line passing through the North Pole intersects a section at point P and makes a corresponding intersection on the other section. For showing the metric structure of the sections, we choose 3 points close to each other such that they make similar triangles in every section. Dirac-Scissors problem says that a continuous rotation of the structure through 2π changes the sign of the half-plane that is attached to it. This is a 1-to-2 relation between a restricted Lorentz transformation and the special linear group of complex dimension 2 up to a boost. The topology of the relation is like the 1-to-2 relation between the special orthogonal group of real dimension 3 and the special unitary group of complex dimension 2. The geometric structure of similar triangles with vertices P, P', and P'' undergoes unrestricted spin transformations. The null flag bundle f of M and its twofold covering space, the spin vector bundle f', are shown. The bundle projection map sends a null flag to an event in spacetime M. Null flags in the fiber space are 4-dimensional, which make the total space of the null flag bundle 8-dimensional. The map to R4 of future null cone and null flag provides in continuous fashion a unique frame ABCD. Construct a unique frame that is right-handed and orthonormal with respect to the Euclidean metric of R4. What is the relation between a spin frame and a Minkowski tetrad? A spin frame is in a vector space over complex numbers. The spin space has the axioms of an abstract vector space. If a spin vector is in S negative, then under restricted spin transformations, It does not leave the sphere S negative to S positive. A spin vector is a ratio between two complex numbers, along with a time sign. Spin vectors exist in a spin space that is equipped with three operations: scalar multiplication, inner product, and addition. Unless an unrestricted Lorentz transformation is applied, spin vectors remain in either the sphere of past null directions, S negative, or S positive. In the sphere of future null directions, S positive, a circle connects 3 points, the north pole N, point P, and point Q. At point P, a tangent vector is denoted by L. Also at point Q, a tangent vector is denoted by M. Any circle on S positive through points P and Q makes the same sum of angles with arrows L and M. The inner product of two spin vectors omega and kappa is a complex number. When they are combined in a linear fashion, the flagpoles of omega and kappa span a two-plane. Perform these 4 steps in order to calculate the argument of the scalar product. Step 1. Use the Gram-Schmidt orthogonalization method to find the orthogonal complement of the two-plane. Step 2. Find the intersection of the planes of kappa and omega with the orthogonal complement two-plane from the previous step. Step 3. The flag plane of kappa intersects along the line U, whereas the flag plane of omega intersects along the line V. Step 4. Find the angle between U and V to measure the argument of the inner product. Pi plus 2 times the argument of the inner product of kappa and omega, modulo 2 pi. The addition of spin vectors kappa and omega results in another spin vector kappa plus omega in the spin space. The tails of the flagpoles of kappa, omega, and kappa plus omega are in a circle. The circumcircle of the triangle made by joining the 3 spin vectors makes the same angle with each of the flagpoles. This shows the sum of spin vectors in a special Lorentz frame that brings out the symmetry at a spacetime event. In this inertial frame, we have 3 mappings in a circular fashion. Kappa maps to minus omega, omega maps to kappa plus omega, and kappa plus omega maps to kappa. This way, the flagpole pair and their sum are collinear in the argand plane. This special frame brings out the symmetry of spin vector sum. In this frame, we have 4 mappings in a circular fashion. The 2 spin vectors, along with their sum and subtraction, are all in a straight line in the argand plane. The fact that there are 8 gluons, 3 weak gauge bosons, and 1 photon is related to the dimensions of the Lie groups SU3 and SU2 cross U1. Connections on principal bundles correspond to gauge fields, whose particle excitations in the associated quantum field theory are the gauge bosons that transmit interactions. Gauge fields correspond to gauge bosons, spin 1 particles, and are described by 1 forms, or dually vector fields. Spacetime is a pseudo-Riemannian manifold M endowed with a metric tensor and governed by geometrical laws. Over M is a principal G bundle X with a non-abelian gauge group G. Fermions are sections of S hat positive tensor product V sub R, direct sum S hat negative tensor product V sub R tilde. R and R tilde are not isomorphic. Their failure to be isomorphic explains why the light fermions are light and presumably has its origins in a representation difference delta in some underlying theory. Matter fields in physics are described by smooth sections of vector bundles E associated to principal bundles P via the representation of the gauge group G on a vector space V. In the case of fermions, the associated bundle E is twisted in addition with a spinor bundle S. That is, the bundle is S tensor product E. These particles are fermions, spin 1/2 particles, and are described by spinors. In physics, the commutator of A sub mu and A sub nu in the expression for the curvature 2 form F sub mu nu is interpreted as a direct interaction between gauge bosons described by the gauge field A sub mu. The commutator of the connection 1 form leads to cubic and quartic terms in the Yang-Mills Lagrangian. Given a spin structure on a pseudo-Riemannian manifold and the spinor bundle S, we would like to have a covariant derivative on S so that we can define field equations involving derivatives of spinors. There is a Cartesian product M cross V above a local open region of the base manifold. In a trivial bundle, the points of the fiber bundle are tuples of elements in the base M and fiber V. In the case of a non-trivial fiber bundle, use multiple coordinate charts to cover the base manifold M. Suppose that the base manifold M is the skin of the globe. Further, suppose that the fiber manifold V is a one-dimensional vector space. Then, the total space of the trivial bundle is like a torus revolution, whereas the twisted bundle is like the Mobius strip. The clutching construction makes a vector bundle over the sphere. The twist occurs at the boundary of the two charts. The clutching construction gives a continuous vector field globally. A cross-section of a bundle is a continuous image of the base manifold. A section intersects each individual fiber in a single point. The bundle projection map of a section gives the identity. The complex plane extends to infinity in every direction from the origin. But in the Riemann sphere, all directions from the North Pole end up at the South Pole in Antarctica. The line bundle can have a global section, where in fact the Clifford bundle can't have a global section. Let Q be a unit quaternion number and its antipodal point minus Q, it's negative. The point Q is in the unit circle, which is embedded in the two complex dimensional plane. In the plane C2, the unit 3-sphere coordinates assert that the squared norm of W plus the squared norm of Z equals 1. The fibers of the tangent bundle to S2 are circles, but each circle fiber of the Clifford bundle wraps twice around each circle fiber of the tangent bundle to S2. Wrapping around each circle fiber of the Clifford bundle once yields the antipodal point in the 3-sphere. In the complex 2-plane WZ, the unit circle is given by the equation the squared norm of W plus the squared norm of Z equals 1. The complex line bundle is the entire complex line, given by A times W plus B times Z equals 0, where A and B are complex numbers. In the complex line bundle, the base space is the ratio A to B, which is proportional to the slope of the line. Use the exponential function for translation along a direction in the tangent space to get a tangent vector at Q. Specify a cross-section of the tangent bundle in order to have a nowhere vanishing vector field. Define a one-form by fixing one of the arguments of a scalar product, using elements from the nowhere vanishing vector field. In order to go from a fixed point to another fixed point along the circle, two paths of different lengths are possible. In the strained bundle, two horizontal flows are combined with a third flow in the vertical direction. Measure the strain in the plane fibers with a connection on the fiber bundle. A tangent vector at a point in the base manifold R2 is represented by a particular point in the fiber manifold S1 above it. A horizontal curve in the tangent bundle of R2 represents the parallel transportation of some vector along a curve in R2. Constant transport in the base R2 is defined from a notion of horizontal in the circle bundle R2 cross S1. How to make the connection of a strained line bundle over S1? Step 1. Remove a point from circle S1 to get a trivial region above it. Step 2. Apply a linear transformation to the fibers of a copy of the trivial region. Step 3. Identify the endpoints of the two trivial regions after splitting, such that they make the circle whole again. A connection measures the scale difference in fibers above one of the regions compared with sections above the other region. The bundle curvature is shown as a horizontal loop fails to close above the unit circle. A complex number denoted by z sets the coordinates of a point in the base space C. The unit circle S1 in C is parameterized with z equals the exponent of I times theta. We use the explicit connection nabla equals the partial derivative with respect to z minus a, where a is a complex smooth function of z. If function a is complex differentiable in a neighborhood of point z, then the bundle curvature vanishes. But if a equals I times k times z, then for the part of the bundle above the unit circle S1, we get a real stretch with a given value of k. One can also extend the symmetry of the fiber space into a two-dimensional real vector space. The fiber space can have a complex structure to make it a one-dimensional complex vector space. In that case, a complex stretch twists the connection nabla with multiplication by a complex number c. Let Q be a point in a principal G bundle and A a connection 1,4. Suppose that the point Q is a vertex of an infinitesimal parallelogram where two of the edges intersect. Then the loop integral of the connection A along the edges of the parallelogram equals the exterior derivative of the connection. F sub A equals the exterior derivative of A. Under gravity, a sphere of test particles deforms into an egg-shaped closed surface. From the Newtonian inverse square law, we know that gravity preserves the volume of the surface. Delta R sub mu nu equals 0. Whenever matter is present, R not equal to 0, then a volume-reducing force field deforms spacetime too. Einstein's spacetime has 4 degrees of freedom, where objects in freefall move along geodesic curves. If the loop integral of the gravitational work one form does not vanish, a trajectory is stretched, but the stretch changes the spacing of the stack representing the one form. The deviation of geodesics means that the Hamiltonian flow lifts a circular path to a spiral trajectory. He discards the Weyl curvature as R sub mu nu measures the stretch and its trace measures density. Finally, sets the total matter energy equal to a combination of the Ricci R sub mu nu and scalar R curvatures. So, a stick figure walks along Penrose steps or the Escher staircase, seemingly going upward forever. First, Dirac forms define a Dirac mass term in the Lagrangian for all fermions and, together with the Dirac operator, the kinetic term and the interaction term. Then, the Higgs mechanism of mass generation for gauge bosons and fermions are done through Yukawa couplings. Finally, scalar products construct the gauge invariant Yang-Mills Lagrangian. Each point in the configuration space represents a possible configuration of the chassis, reaction wheel, and rolling wheel. As the system evolves in time, a sequence of telemetry frames makes a curve in the configuration space. The behavior of the robot is constrained with a function that is defined on the tangent bundle of configuration space. The total space of the Clifford bundle is located at a single spacetime event. As an example, the Yang-Mills Lagrangian is the scalar product of a differential form on a principal G bundle with itself. Alternatively, the Hamiltonian is defined as a smooth function on the phase space, also known as the cotangent bundle of the configuration space. One derives the equations of motion for mostly kinetic particles, such as photons and neutrinos, using Hamilton's principle. A particle moves through the configuration space such that the integral of the Lagrangian along a path between two fixed points is stationary under variations of the curve, but the Yang-Mills Lagrangian is an adjoint invariant scalar product of the curvature 2 form on a principal G bundle over spacetime. The adjoint bundle is an associated vector bundle to the principal G bundle, whose values represent the difference between two connections. Geodesic curves describe the shortest distance between two fixed points in a smooth manifold. The exterior derivative of a scalar field at a stationary point is very small in every direction. The tangent bundle of the configuration space of a dynamical system has geodesic curves, along which the integral of the Lagrangian is stationary. The Hamiltonian flow is a section of the cotangent bundle of the configuration space. The Newtonian time evolution of a particle in free fall follows a geodesic trajectory in the configuration space. The stack of equally spaced parallel planes represents the gravitational work 1 form, and its direction is downward. In 1583, Galileo observed that the period of small oscillations is independent of the maximum distance away from the stable equilibrium point. As it turns out, acceleration and position transform in a linear way after expanding a power series of the Hamiltonian about the equilibrium point. Since the pendulum rotates as a special orthogonal group, the pendulum's Newtonian time evolution is unitary. The boundary of the phase space represents a range of possible initial momentum states. The shape of the boundary is distorted during the time evolution of the physical system. Liouville's theorem states that the Hamiltonian flow preserves the volume of the initial phase space boundary. The value of the Hamiltonian function is constant throughout the motion, which implies the conservation of the sum of kinetic and potential energies. In order to reduce the phase space, subtract a partial component of momentum as a result of projecting momentum onto the line tangent to the trajectory. It's remarkable that the reduced phase space can be the configuration space of a physical system. The Yang-Mills Lagrangian is the magnitude of a 2 form with respect to a connection 1 form on spacetime. The 2 form has an exact symmetry, if and only if it is equal to the loop integral of a 1 form along the boundary of an oriented area. But if this 1 form exists, then the integral introduces a scalar constant, and one has the freedom to transform the gauge as a reference level. The boundary of a well-behaved compact-oriented 4-dimensional region is a 3-dimensional region. The boundary consists of those points of the 4 region that do not lie in the interior. Hamilton's principle states that the integral of a 4 form scaled by some field Lagrangian over a 4-dimensional region is stationary. What are horizontal subspaces, and what do they have to do with vector potentials and gauge fields? A connection denoted by A on a principal G bundle P assigns a horizontal subspace of the tangent space to each point Q in P in a smooth way. First, the tangent space of a principal bundle P at point Q is equal to the direct sum of the vertical subspace and the horizontal subspace at Q for all Q in P. Second, the push forward of the horizontal subspace of the principal G bundle P at point Q by an action G of the structure group G is equal to the horizontal subspace of the principal G bundle P at the transformation of the point Q by the action G for all G in G and Q in P. If the exterior derivative of the curvature 2 form vanishes, then there exists a 1 form potential that acts as a reference level. The vector representation of the 1 form is called a vector potential, but the 1 form on spacetime is called a gauge field. So, geometrically, the vector potential is normal to the stack of horizontal planes of the 1 form.